Beneath the vast oceans, hidden webs of fiber optic cables stretches for hundreds of thousands of miles, forming the unseen backbone of the internet. These cables carry almost all the world's data, transmitting information at the speed of light. But with the increasing use of AI and video streaming, the demand for data is skyrocketing, and a single fiber optic strand can only carry so much data. So how do tech companies squeeze more and more data through these undersea highways? The answer lies in groundbreaking technology called DWDM, dense wavelength division multiplexing. This powerful innovation allows a single fiber to carry not just one stream of data, but dozens or even hundreds of data streams simultaneously, each traveling on its own unique wavelength of light. This is like turning a single-lane road into a multi-lane highway, exponentially increasing capacity without laying new cables. The visible light that we see from the sun can be split into various colors. Each of these colors of light have their own wavelengths on the electromagnetic spectrum. The solution engineers found was to split the light entering a single fiber into dozens of wavelengths, each carrying its own data stream. Fiber optic cables are made of super thin strands of glass or plastics wrapped in protective layers. Data is converted into pulses of light that bounce through the fiber optic cable via a phenomenon called total internal reflection. And unlike electrons traveling through copper cables, light traveling through fiber optic cables maintains its strength remarkably well, even across thousands of miles. The first of the light wave splitting technologies was the TDM, time division multiplexing. TDM divides the capacity of single fiber into time slots. This was the leading technology in the telecom sector from the 1960s through to the 1980s. Wavelength division multiplexing, WDM, emerged in the 1970s. It utilized 2 to 8 light wavelengths in a fiber to transmit data, but didn't quite meet the density requirements. A simplified variant, coarse wavelength division multiplexing, CWDM, was introduced as well, featuring wider channel spacing for short-distance networks like rail metro systems. But more data speeds was required, and so in the early 1990s, the dense wavelength division multiplexing, DWDM, was born. DWDM is a fiber optic transmission technology that combines multiple data-carrying light wavelengths onto a single optical fiber. Every wavelength acts like its own channel, allowing for huge data capacities across long distances. Think of it like a road that has been turned into a multi-lane highway where each lane carries its own traffic smoothly without any interference. Russia also has companies that create DWDMs. T8 was created in 2008 as a startup by graduates of the Moscow Institute of Physics and Technology in the Skolkovo Business Incubator. Today, T8 dominates Russia's DWDM market, deploying over 100,000 kilometers of fiber networks and offering products for backbone networks, metropolitan networks, and data center interconnects. They have been involved in the construction of backbone fiber networks in Siberia, St. Petersburg, and the Volga regions. T8 occupies about 45% of Russian DWDM market, competing mainly with Chinese companies. Among its customers are the largest telecoms operators like Rostelecom and mobile operators like MTS, Beeline, Megaphone, and Tele2. The company has also implemented projects in neighboring countries like installing DWDMs and optical amplifiers in Kazakhstan. Other notable Russian DWDM companies include VPG LaseOne, Neoros, and Supertel. VPG LaseOne offers a 600 GB per second wavelength device called Horizon, while Neoros brings the NR1008 DWDM platform, also featuring 600 GB per second per wavelength, ideal for both metro area and long-haul networks. Supertel's DWDM is called the OptiPack 2. DWDM technology has been fully democratized. The global leaders are Huawei, Nokia, and Ciena. Indian companies focus on cost-effective localized solutions for regional networks and government use cases. The Russian company T8 is catering to fight for dominance against the Chinese in the Russian market while seeking leadership in Central Asia and former Soviet bloc countries. DWDMs come with special features. Let's explain some of these features. ROAD-M stands for Reconfigurable Optical Add-Drop Multiplexer. This feature allows wavelengths to be added, dropped, or routed on-site, making the system more reconfigurable and enabling network operators to remotely provision network traffic. FlexGrid. This feature enables variable channel spacing of wavelengths for more efficient spectrum use. FlexGrid is now mandatory for 800G and 1.6 TB networks. Proprietary DSP chips. Some DWDMs are powered by in-house designed custom chips that facilitate higher transmission speeds. Ciena's exclusive digital signal processor chipset is called the WaveLogic DSP. Nokia's is the PSE6 and Huawei is ODSP. IP over DWDM. IP over DWDM integrates IP routing within the optical layer. Ciena calls its version adaptive IP, with Huawei calling its version OptiTrans OTN switching. Comparing DWDMs from public information is difficult, but units from Huawei, Ciena, Nokia, T8 and ZTE all seem to have top wavelength capacity of 800 GB per second per wavelength. The units from China's FiberHome and Indian manufacturers Tejas and UTL have less wavelength capacities at 400 GB per second. Huawei has a model with the highest number of channels at 120, and the rest of the companies have units of up to 96 channels. The maximum throughput for units of Ciena, Huawei, T8, ZTE is around 38.4 terabits per second. Most operators seem to regard Huawei and Ciena's offering the best balance between capacity and programmability, while Nokia provides the most flexibility and reconfigurability, good for metro, regional, and core networks. DWDM sits at the foundation of today's networks. It powers the physical layer that carries all the data for upper layer protocols like IP, Ethernet, and OTN. By enabling terabit-scale data transport over existing fibers, it ensures seamless connectivity to everything from telecom operators to global cloud service providers. DWDM allowed internet to grow exponentially without the need for constant digging for new fiber lines. Today, DWDM systems underpin AI searches, 8K video streaming, and virtual reality by delivering petabit-level capacity. The first DWDMs that appeared in the 1990s transferred up to 1 terabit per second. The 2010s with coherent optics transferred 20 terabits per second per fiber, and the 2020s with special division multiplexing SDM is transferring about 100 terabits per second per fiber. Ciena will soon be introducing the next generation of DWDMs, moving from 800G to 1.6 terabits per second per wavelength. A new company, Mavel, has introduced a 3nm Mavel Ayar chip that supports 1.6 terabits per second, offering higher performance whilst reducing power consumption. In the near future, companies like Ayar Labs with optical I/O chips are merging photonics and semiconductors to offload some of the functions of photonic processors, thus increasing speed. Intel is also creating silicon photonic transceivers by integrating CMOS with photonic integrated circuits. DWDM will remain the backbone of global connectivity, evolving with innovations like photonic integrated circuits and machine learning-driven network optimization. Its creation marked a turning point in telecommunications, making the modern internet economically and technically feasible. Subscribe and stay tuned.